In this video, I'd like to do two things. We'd like to discuss how to determine the empirical formula for an ionic compound for any given set of ions, cations and anions. And then I'd also like to show you how to determine for common ions their ionic state for the various atoms as a function of their position on the periodic table. So in other words, can we predict what is the likely charge for a sodium when it ionizes? Or can we predict the likely charge for chlorine in an ionic compound as chloride? So we're going to do those two things, and then in a subsequent video and in other practice, we'll be looking at how to determine the charge of the ions in a compound from their empirical formula. So basically the opposite direction of steps 1 and 2 that we're looking at. Now, the empirical formula, as we discussed in the previous video, is based on the lowest ratio of cations and anions that can produce a neutral compound. So we want charge neutrality when we put together these ions to make the ionic compound. So for instance, the ionic compound or salt formed from sodium ion, which is Na+, and oxide ion, which is O2-, requires that the ratio of sodium and oxide be such that we get a neutral salt. So how do we determine what in this one it's probably pretty obvious that we need 2 sodiums per oxygen. One quick way of doing this is to write arrows across from the charges down to the subscripts that will become the number of ions in the ionic compound's empirical formula. So we just do crosses like this and then get a formula for this ionic compound of Na2O. Now that Na2 refers to the fact that there are 2 sodium ions, right? 2 Na pluses per 1 O2- in the extended network of the lattice. So that is the ratio of sodiums to oxides in the whole lattice, which we talked about in the previous video. The positive charges, of course, of the 2 sodium ions here balance the -2 charge of the oxide. Another example, what is the empirical formula for the salt formed by aluminum, which is a 3+ ion, and chloride, which is a 1- ion. So aluminum cation, chloride anion, cross. So there is going to be an empirical formula of aluminum, 1 aluminum ion to 3 chloride ions, AlCl3. And of course that means that for every 1 Al3+ in our lattice, there are 3 chloride ions to balance to give a neutral compound. What we'd like to do next then is to give you a little insight into how to determine the ionic state for various atoms as a function of their position on the periodic table. And so we can use the periodic table as a guide to help us remember what are the common ionic states, in other words, the common charges of various elements when they form ions. So in the first column of the periodic table, we have helium, lithium, sodium, potassium, rubidium, and cesium. Excluding hydrogen, these are all metals. And we have in the second column of the periodic table beryllium through barium. These are also metals. Next in our periodic table is the transition metal region, which we'll talk about in the last part of this video. When we count over to column 13, through all the 10 transition metal columns to boron's family, essentially, We have boron through aluminum, gallium, indium, and thallium. 14 brings us to carbon's family. 15, nitrogen. And what you're seeing here is that I have in purple metals, and in brown or darkish orange are nonmetals. And we see here, as we move even further to oxygen family, that as we proceed from left to right across the periodic table, there's a transition from metallic structure to or metallic type of elements to nonmetals. And of course, elements like silicon and germanium and arsenic and antimony are sometimes considered semi-metals because they're right at the transition area in the periodic table as things go from metallic to non-metallic. Continuing, we have the halogens, and then we have the noble gases. Now, just to recap, metals here in purple, nonmetals in brown, and recall that ionization for elements in the periodic table, in other words, the energy to remove an electron from an element, an atom of an element, increases up and to the right. So up and to the right, we have increasing ionization energy. So up and to the right in the periodic table, it becomes more and more difficult to remove electrons. And so for this reason, metals, when they react, tend to lose electrons and form cations. So in the formation of an ionic compound, that's why we see most of the metals are forming cations, species with the positive charge in the structure. Nonmetals, because they're much more difficult to ionize by removing electrons, instead gain electrons. And this is this ability to gain electrons is more common for the nonmetals, because of the fact that you get some energy back when you add an electron to those, and that's called the electron affinity for the nonmetal. But the takeaway point here is that we have metals on the left-hand side of the periodic table with relatively low ionization energies, and therefore they will more readily lose electrons to form cations. And we have the nonmetals on the right-hand side of the periodic table, where they have higher ionization energies and are more than difficult to remove electrons from. And then, of course, in reactions that form ionic compounds, they tend to be the ones that are gaining the electron and becoming negatively charged anions. The number of electrons that can be lost or gained depends on the position of the element in the periodic table and the total number of valence electrons that particular the atom of that element has. So, for instance, we know that in the first column of the periodic table, the alkali metals, lithium, sodium, potassium, rubidium, cesium, they all have one valence electron, right? Because they're the first step in the periodic table. Each has one valence electron. In the second family of the periodic table, the alkaline earth metals, we know that each of those has two valence electrons. So, lithium, because it is on the left-hand side of the periodic table and a metal, can easily give up a single electron, the valence electron, to form lithium plus ion, cation. Now, it doesn't give up more electrons than that, because in order to do so, we would have to dip into the core electrons, and the ionization energy, as we saw in previous lectures, increases drastically as we try to remove core electrons. But the valence electrons for metals are relatively loosely held with the low ionization energies, and so we can have this type of reaction. Lithium losing one valence electron to form lithium plus. And of course, I'm going to put that into the periodic table here. Okay. We see that, of course, similar reaction with sodium, right? Because sodium also has only one valence electron with a fairly low ionization energy. In fact, a lower ionization energy than lithium because it's further down in the periodic table. And so can form sodium plus by removing that one valence electron. And of course, that's the case with all of the elements in of the alkali metals. They each have one valence electron which they can lose to form a positive charge. And so you see here that the metals in column 1 of the periodic table will form +1 ions in reactions in which they form salts or ionic compounds. Beryllium with 2 valence electrons can lose up to 2 electrons to form beryllium 2 plus, as shown here. And so, and of course, adding that to the periodic table here, we'll remove those 2 valence electrons. And we remove 2 electrons. Now I have the balance of charge in that atom is going to have 2 more protons than electrons, and therefore a 2 plus charge. And of course, that will be the case for all of the elements in that family. So we have beryllium 2 plus, magnesium 2 plus, and so forth. Now, why do not beryllium, magnesium, calcium lose more electrons than 2? And that's because if we were to when we remove the first 2 electrons, those are the valence set. To remove more electrons, we'd have to go to the core electrons, which are much more tightly held to the nucleus. And so the ionization energy for core electrons is prohibitive to removing them. And what this means then is that the column 2 elements form +2 ions. Now we're going to skip over to column 13, and we're going to talk specifically about aluminum. Aluminum has 3 valence electrons. It's a metal with a fairly low ionization energy, and therefore it can lose those 3 to form a 3 plus ion. And that is the common oxidation state for aluminum. Moving over to column 15, nitrogen and phosphorus both have 5 valence electrons, but of course now you can see that we're on the non-metal area of the periodic table. These have much higher ionization energies, and they hold on very tightly to those 5 valence electrons. However, in a reaction with a metal, which is readily giving up electrons, they are happy. I say happy, it's energetically favorable for them to take the electron from those metals. Okay, so with the 5 valence electrons, that non-metal has, for nitrogen's case, it's going to gain electrons, and it has positions for 3 electrons. Now, what do I mean by it has 3 positions? It can gain 3 electrons to complete its valence set of 8. So as we see here, the nitrogen has 5 valence electrons, so 3 open spots to fill its valence set. So I add 3 electrons, and those are shown in red. Those 3 electrons are now surrounding this Lewis structure for this ion, which now has 3 extra electrons and therefore a 3 minus charge. Okay, let's go back there. So now we have 3 minus charge. That is also the case for the other elements in the nitrogen family. So phosphorus will form 3 minus anions with a 3 minus charge in ionic compounds. Next we move on to oxygen's family. Oxygen has 6 valence electrons and therefore 2 open spots from which it can take electrons from metals in forming ionic compounds. Sulfur is the same. Sulfur has 6 valence electrons. So both of those with their 6 can gain 2 electrons to complete their valence set. When I add those 2 electrons in here, so up in the periodic table I'm showing the 2 extra electrons, now that becomes from oxygen to oxide with a 2- charge. And then sulfur, gaining 2 electrons, becomes 2- and sulfide. And of course that continues for the other elements in that family. Moving on to the halogens, we see that we have 7 valence electrons for fluorine, chlorine, bromine, iodine. They each have 1 spot, so they can gain 1 electron to complete their valence set of 8. So there is fluorine 7, adding 1 electron gives it a -1 charge, and that's the case for the rest of the halogens as well. So now looking across the periodic table, we see this trend, right? We have the metals with the positive charges, so the alkali metals, the alkali earth metals, +1s and +2 charges on each of those. Aluminum with its set charge of 3+, and then we get over to the nonmetals. Starting at nitrogen family, we have 3-, to the oxygens family 2-, and then the halogens at 1-. And of course, the noble gases are set with 8, so they tend not to gain or lose electrons. They're pretty satisfied the way they are. The charges on the transition metals are a little bit more complex. They don't have these set charges the way many of the other elements do that we've already covered. Transition metals, due to the electrons, can have a few different, what we call oxidation states. So for instance, iron is commonly either +2 or +3, depending on the compound. So filling that into the periodic table. And there's actually some other oxidation states of iron that occur in many biological systems, going higher than +3. Copper is commonly either +1 or +2. Cobalt, +2 or +3. Zinc, because it's on the end of the transition metals, has only 1 common charge, and that's 2+, so that one's easy to remember. In addition to the transition metals, some of the other larger metals in the in groups 13 through 16 also have multiple charge states. So thallium, for instance, can be +1 or +3. Lead is often +2 or +4, and so forth. Keep in mind, as I was mentioning earlier in the video, ionic compounds form due to a transfer of electrons. So before I showed a single element gaining an electron to become negatively charged, I showed the electron in the formula. But of course, what's really going on in reactions is that an electron is transferred. So here, what I'm showing is a potassium with 1 valence electron, and oxygen with its 6 valence electrons. And as we said, oxygen, a non-metal, right, likes to gain electrons. Potassium, being a metal and having a fairly low ionization energy, can give up that electron to oxygen. Oxygen has 2 spots, and so therefore, let's do this a little bit slower. Oxygen has 2 spots, right? So I'm going to need, right, 1 electron from 2 potassiums to donate to oxygen. Those 2 electrons will, right, complete oxygen's valence set of 8 to give a 2- oxide. I'll be left with 2 +1 potassium ions. Okay, so here's the final sort of Lewis representation of that reaction. Okay, so now let's go back to what we were doing in the previous video, which is to determine the empirical formula, now with the knowledge of the common oxidation states for these different elements when they're in ionic compounds. So, what is the formula for the ionic compound is formed between aluminum and oxygen. So I have a reaction between aluminum and oxygen. It's going to form aluminum oxide. What will be the formula for that aluminum oxide ionic salt? Well, we know from the periodic table that, looking up at column 13, aluminum, right, based on its 3 valence electrons and the fact that it's a metal, can give those 3 up to form a +3 charge. Oxygen with 2 empty valence spots will gain 2 electrons to become 2 minus. And then we're going to use the sort of cross method to determine what the ratio of aluminum ions to oxygen ions will be, aluminums to oxides, and that is 2 to 3. So the structure for this compound is aluminum oxide is Al2O3, and that will give us a neutral aluminum oxide salt.